This is the video for the problem solving unit. This is using ratios and proportions to do problem solving. With a lot of problems can be solved using ratio and proportions or some form of them. So, in general, a proportion is the comparison of two ratios. A over x is a ratio and b to c is a ratio. And we know that to solve a proportion, when you have two equivalent ratios, you can multiply what are called the means and extremes. So that is, a times c should be equal to b times x or x times b. And so if you were solving for x, in this case, you'd divide both sides by b. So a lot of times we just kind of shortcut that and say we cross multiply these two known values and divide by b, the other known value. So if you're looking for x, you cross multiply the other two and divide by the one that's diagonal to x. So x is just ac over b. So in this case, if you're solving for x, you cross multiply those two numbers and divide by 8. So we just simply get 3.5 times 5.2 divided by 8. And it's that simple. So solving a proportion, once it's set up, is easy. What you need to make sure you do is, when setting up a proportion in an application, corresponding units should be aligned in the proportion. So for example, with a problem involving dollars and gallons, and A is to B as C is to X, then we say if it's A dollars to B gallons, so many dollars for so many gallons, then C dollars would correspond with X gallons. So notice dollars to gallons, dollars to gallons. And again, if we're solving for X, we're going to cross multiply the other two on the off diagonal. So X will be equal to the B times C divided by A. Now I didn't put the units in there, but what would happen if you put gallons and dollars there with the B and C and dollars here, they would all drop out and you'd get gallons. That is, you'd get, it would be B gallons and C would be dollars, and then we divide by A dollars, and notice the dollars would reduce and our final answer would be in gallons, and that's what X is supposed to be, and the units for X is gallons. Okay, so let's take a look at an application. We can use that corresponding unit idea and simply set up a proportion, cross multiply and divide. So when you are walking on a treadmill, the readout indicates that after 10 minutes of brisk walking, you have burned 60 calories. Now that's a comparison, 10 minutes compared to 60 calories. It says at that rate, and proportions rely on you maintaining the same rate, approximately how long would it take you to burn 800 calories through brisk walking? So if we take 10 minutes to 60 calories, that is a ratio. It's really a rate because they're different units. 10 minutes and 60 calories. That would be equivalent to how many, now this should be minutes here because we got minutes in here and calories down here. So what it asks for is how long would it take to burn 800 calories? Well, the 800 calories would have to go down here because we have minutes to calories, and X would be the number of minutes to burn 800 calories. That's what we don't know. So we will cross multiply the two known values opposite of the X, not on the opposite of X, and then divide by 60. So X should be cross multiply those two known values, 10 times 800, and divide by 60. So we could do some little reducing here. We could have reduced 10 and 60 actually right at the beginning of 1 over 6. But we can reduce it here too, divide both of those by 10, and we'd end up getting 1 times 800, which is 800 over 6. Now this said just approximately because, we don't burn calories at exactly the same rate. So I'm just going to take 800 divided by 6, which is 133.3 repeating. That's what that would be if we did it exactly. And that should be in minutes, because this 10 would have been in minutes. The 800 was calories, the 60 was also calories, and the calories would drop out, and we would have been left with 10 minutes. So it's about 133.3 repeating minutes, or 120 minutes is 2 hours. So you could, if we took away 120 minutes, that would be our 2 hours. That would leave 13.3 minutes left. So I would say about 2 hours and 13 minutes. That would be our approximation. Okay, approximately. You can't really sustain the same exact rate when you're burning calories and walking. Okay, so that's problem number 1. Now let's take a look at another problem. It says the Wild Horse Wind and Solar Facility has the capacity to produce 273 megawatts, which is enough to provide power for 63,000 homes in central Washington. So Wild Horse is a wind generating, primarily wind, but it does have solar as well. So the big wind generators that you see up by Vantage on the way from Ellensburg to Vantage, a lot of those are from Wild Horse. There's actually another facility that has wind generators there also. But how much power would it take for nearly 3 million homes in the state of Washington if the power needed was similar throughout the state? So 273 megawatts provides enough power for 63,000 homes. That's a rate that compares this much power to this many homes. And now they want to know how much power to generate for 3 million homes. So if we do this, set this proportion up, 273 megawatts and 63,000 homes. Over here on this other ratio, we're going to need to have megawatts up here and homes down here. So we don't know, we know that we have 3 million homes. I guess I'll write that out. That's a 3 with 6 zeros. And we don't know how many megawatts we'll need. So if we're solving for this x, we'll cross multiply these and divide by this. So we know we'll get megawatts in homes over homes, so the homes will drop out and our answer will be megawatts. So we can just multiply x, we can multiply 273 times the 3 million and then divide that by 63,000, and we can divide both of those by 1,000. That'll drop out 3 of those zeros. And now we can take 273 times 3,000 divided by 63 and see what we get. So that will be 273 times the 3,000 divided by 63. And that gives me 13,000. So that is 13,000 megawatts. Pretty straightforward. Now part B asks how much would be needed in the USA where the number of homes is over 125 million. We would set that up and do it the same exact way. We could still go back to 273 megawatts was enough to power 63,000 homes. And now we would set that up with, instead of 3 million homes, we have 125 million homes. So basically we'd have, how many megawatts would that be? Instead of 273 times 3 million, we'd have 273 by 125 million. So our x would be the same exact thing. 273 times 125 million all over 63,000. And so basically the same exact problem. I can go back and just edit what I wrote in my last calculator. I can just put in 125 instead of 3,000. And I'm getting 52,000. That doesn't sound right. Yeah. Yeah, 273 times 125,000. divided by 63. Yeah, I got only 52,000 first time, but this is 541,666.6 repeating. So I'm going to just say that's about 541,666 repeating. I'm just say 670 megawatts, and it just wants an approximation anyway. Okay, so those are pretty straightforward. Now, let's look at this one. This is a little different. This is still on watts as a power system. So this says if 7,500 watt solar array costs 28,500 to have installed, how much will it cost to have an 8.5 kilowatt array installed, assuming a consistent rate per watt for installation? Well, if this is in watts for 28,500, this is kilowatts. Usually we use a capital K, but 8.5 kilowatts would have to be converted to watts first. So you need to know that there are 1,000 watts in 1 kilowatt. You'll need to know this for the test. I won't give you the conversion for 1,000 watts is 1 kilowatt, but you get an 8.5 by 11 note sheet, so you can include that on your, you can include this fact on your note sheet, so you can refer to it if you have to do a conversion from kilowatts to watts. So our kilowatts reduce, and when you multiply by 1,000, that moves the decimal 3 places to the right, so that's 8,500 watts. So now we have a 7,500 watt array, costs $28,500. Then this should be in, I'll just leave that there, watts per dollars here. So our X, whatever we get for our value there, this should be in dollars. Watts to dollars, watts to dollars. And those are equal. So here's X, we're going to cross multiply and divide. So we cross multiply those diagonals, 28,500 times the 8,500 divided by 7,500. Now we could have reduced these zeros here by dividing by 100. We could reduce the zeros here anytime. We can just drop that off, right? That's dividing both by 100. And we could reduce more if we wanted, but we get a calculator, so why not just use it? So 28,500 times 85 divided by 75. That's 3,000, I'm getting, this is our X. It's $32,300. Now that should make pretty good sense because 8.5 kilowatts, it's not that much bigger than 7,500 watts. Because that's 8,500 watts. So a little bit more, and it costs a little bit more. Are there other ways to do this? Absolutely. You could find out how many dollars per watt it costs, and then just multiply by 8,500 watts. This is just the method of using proportions to solve that. Okay, we're going to take a break, and then come back and do some just unit ratio conversions and rate conversions in the next video.